Okay, we are now dealing with work. In physics terms, work is the product of force and distance. So notice that I've said in the past that you can define a physics concept with a whole bunch of words, right? So notice all the words that we use to define this concept work. Or we can alternatively define it mathematically in a very simple fashion, W equals FD. Notice how simple this is. Now the reason why I'm particularly making this point, as I have before, is because some fraction of the students who take this course with me have math anxiety, right? They're freaked out by math and formulae. I'm just making the point that mathematics is very simply a shorthand. Instead of using like tons and tons of words that seem very confusing, you say, what the heck does this mean? We can write it very, very simply. Look, with 4 symbols, W equals FD. Of course, you have to know what each symbol stands for, right? F stands for force, D stands for distance, W equals the work. So, if I were to have a car here, let's say like if you ever ran out of gas and you happen to be pushing a car, which is, okay, to the gas station. Moral of the story, do not run out of gas, right? So what happens is, you apply a certain force on the car and you push and you push and you huff and you puff and you push, right? So, you apply that force over a distance of, let's say, a mile. So you got the distance, and let's say that you're able to measure the force that you applied. So that force multiplied by the distance will be the work that you did on the car. The work that you did on the car will translate into a momentum of the car. The fact that you're doing work on the car is what is getting the car to move forward, right, towards the gas station. So what is happening when you do that work is chemical energy that's stored in you from the food that you ate, right? You're all familiar with ATP, ADP, right? Is anyone here not familiar with ADP, ATP? Adenosine diphosphate, adenosine triphosphate. You don't need to know that for this course, but you know that those are the little battery cells that run around in our system that store up the energy that you get when you eat something, right? So ADP gets converted into ATP. So chemical energy gets stored in the bonds of ATP. ATP is a little molecule that is translated throughout your body through the bloodstream, and it goes into all the cells. So every cell has energy. So when you need energy, like to lift something, what happens is your body, the cells in your muscles, right? They basically call upon ATP. They take ATP and convert it into ADP, take that excess energy from that one bond, and then use it to do something like contract your muscles and that kind of stuff, and that's how you're able to do work. So when you push the car, what's happening is chemical energy in you is then being converted into kinetic energy, if you will, of your motion, which is converted into kinetic energy of motion of the car, right? And that's basically what's happening. So the chemical energy in you is being converted for you to apply a force on the car that travels a certain distance. So the amount of energy that you spend to do this work is coming from the food that you ate in that particular example. Okay, moving on. Okay, so here's a bodybuilder who's lifting these barbells or whatever they are up a certain height, right? So the work that he does is going to be equal to the force that he applies to lift these up multiplied by the distance. So if he lifts this up through whatever, 6 feet or something like that, or let's say 2 meters, right? 6 feet. So 2 meters, that's the distance, and the force would be whatever, 500 newtons. So 500 newtons, let's say, multiplied by the distance gives the work done. That's the work that he has done in lifting up the barbells. That, as I mentioned, that work is basically being done based on the stuff that he has eaten the previous day or stored in his body since. Now here's a convict who's trying to get out of prison, and he pushes really hard on the wall, right? He huffs and he puffs and he sweats and he huffs and he puffs some more, and the wall does not budge. How much work has he done? From a physics perspective, he has done none, no work. And the reason why he has done no work is because the distance traveled by the wall is 0. Therefore, force multiplied by distance, work done is equal to 0. Of course, these are to a first approximation, right? I know that when you try to push against a wall, it feels very much like you are doing work, right? And that's beyond the level of this lecture, because there is relative motion inside your body when that happens. Okay, definition of the next term, power. Power is the time rate of work. What that is how much work you do per unit time. So work divided by time gives you the power. So this is just making the point that a space shuttle develops 33,000 megawatts of power when the fuel is burned to get it off the ground, and it's saying it's burning the fuel at a rate of 3,400 kilograms per second. It's the equivalent of emptying a swimming pool worth of fuel in 20 seconds. So think of your swimming pool, 20 seconds. By the time you say, you count to 20 Mississippi, right? The pool is emptied of fuel, and you have to go and top her off again. Can you imagine how much that would cost? Think of topping up your car, right? And this fuel is like way more expensive than what you put into your car. So again, sorry?
Is the abbreviation for power just P?
You could use P, yes, it's common, yeah. So, extra credit to you for asking the question. You're probably maxed out. Yeah? Okay. Then, extra credit to you to congratulate you on having maxed out. It gives me joy to give you extra. I know you can't use it, but it makes you feel really good about yourself, right?
That's right.
Yes, good. So, power, P, would be the work done divided by time. So, it's force multiplied by distance divided by time. Okay, next, introducing the concept of energy, right? Okay, again, from a philosophical perspective, okay, I'll switch between physics and philosophy. From a philosophical perspective, we do not know what energy is. Notice what it says up there. It says the property of a system that enables it to do work. Have we really answered the question? We haven't. A lot of fundamental definitions in science are like this, where the truth of the matter is we do not know what it is. All that we do is we observe what it does, and we then come up with a description of what it does, and then we say, oh yeah, we think we know what it is, but the truth is we do not, right? But for the level of a physics course, we just take it on faith, if you will, like a building block, right? We just assume that is the case, and then we move on. So, energy is the property of a system that enables it to do work. So there are different kinds of energy. So introducing potential energy, it's like energy that gives you the potential to do something. Versus kinetic energy is energy associated with motion. So coming back to potential energy, this is the energy that a body possesses because of its position. That is not exactly correct. It's based on its position in a field of some kind. So the definition for this is a body in a gravitational field has energy by virtue of its position with respect to the originator of that gravitational field. You don't need to write all of that down, right? For the level of this course, that's fine for you to say it's just related to its position. So the formula for potential energy, PE for potential energy equals mass multiplied by gravity multiplied by height. So this wooden block, let's say it has a certain mass, 1 kilogram. That multiplied by this height, let's say whatever this is, 1 meter. Mass multiplied by gravity, which was what? 10 meters per second downwards. Good job. 9.8, extra credit to you, right? So 9.8 meters per second square. So that's gravity, G, multiplied by the mass, 1 kilogram, multiplied by the height. Let's say that's a meter. It's not. We'll give it potential energy. What happens if I let go of it? It does what? It floats in the air, waiting for me to, right?
No.
I think I'm a skeptic right here. What happens? Does it float in the air?
Falls.
It falls. Extra credit to you. Good job. Why does it fall? Because what?
Because it's pulling down on the earth, because the earth is pulling down on it.
Okay. Because it's, yes. Extra credit for speaking up. And if I didn't, extra credit to you for speaking up. Okay. So you're right. Now you realize we don't understand why gravity works, or why it exists, but we'll take it on faith, if you will. We'll just assume it works. And you're right. Gravity is pulling down. We with you?
It doesn't have to kinetic energy. So.
Okay. Let me finish this and I'll come back. Okay. Good. So if I let go, wow, that woke me up. Right? So notice what happened is the potential energy got converted into energy of motion, kinetic energy. So the object accelerated until it reached some maximum speed. Then when it hit the ground, all that energy got consumed, if you will, by the ground applying the floor applying a force upwards, F multiplied by a very small time. That was the impulse, right, that we saw in a previous lecture. Impulse upwards changed the momentum of the object. The momentum was a consequence of the potential energy getting converted into kinetic energy of motion, right? So all that energy went into two things. Went into the sound that you heard and into vibrations in the floor, right? So there'd be sound waves, pressure waves traveling out on the floor from where it impacted, and the third thing would be heat. There'd be low, the temperature right there and off the block would be slightly higher, maybe let's say a degree higher than degree centigrade, maybe higher, I'm just guessing, probably less than it was prior to that impact, right? So if you look at a meteor crater, an asteroid impact, right? So meteorite or a meteor comes and hits the Earth or the Moon. Actually, you can see that on the Moon, photographs of the Moon. You see this big rays going outwards. Any of you seen that? You can see this big circle of meteor. Like on the Earth, because of the weather, typically a lot of times those are not visible anymore. But on the Moon, because of the absence of kind of air and storms and stuff, meteor hits the Moon and it creates these rays out. And those are because of pressure waves traveling out from the impact, right? And what's happening there? Again, kinetic energy of motion of, okay, this gravitational energy, potential energy of the meteor or the asteroid with respect to the Moon. The Moon attracts it, so the object comes and hits the Moon. The potential energy gets converted into kinetic energy, which then gets converted into energy of destruction. It's basically like creating the crater and the rays and on and so forth.
Inelastic collision.
Those would be, that's correct, an inelastic. Anytime there's deformation, there would be an inelastic collision. Extra credit to you. We miss you.
So back to potential energy and your ATP comment. When the body produces ATP,
Okay.
since chemistry and physics go hand in hand, could you use the same formula to figure out how much potential energy is stored in that bond between the two last phosphates?
That is a really good question.
I mean,
Extra
really
credit.
molecules float around like this, so
Yes.
I mean, height sure, mass sure, but gravity's kind of, I don't want to say it's absent, but it's never going to be they're never going to face towards the Earth every time they're broken apart.
Yes.
Or maybe they do.
Okay, I'm thinking to answer the question that you asked about ATP, ADP, and is it like the energy stored? Like
I'm just asking if
potential
you
energy?
can you measure the amount of potential energy in an ATP, because it only breaks off that last phosphate.
Okay.
Can you measure that amount of potential energy with that formula, or is that a whole different can of worms?
Good question. Extra credit to you. Right now, the same formula does not apply, but a different formula applies, which we will be dealing in a later lecture with springs.
Okay.
So, like, think of a bed spring. You go and sit on the mattress. What happens? Right, it deforms. Right. And when you get up, what happens is the mattress comes back to its original. Right. Okay. So what happens is, as the springs deform, they get compressed. They start applying a force upwards that's proportional to the extent of the deformation. So a heavier person who sits on the bed would lower the bed even more, right? Because the force upwards is increasing proportional to the deformation. The person's weight is higher, they have to deform higher to get the spring to apply the same force. So now the potential energy associated with the spring is half kx squared. K is the spring constant, I was just recalling it, multiplied by the deformation, the extent of deformation squared. Now, molecules can be modeled as springs to a first approximation.
Right.
So there's like a potential well, and you can model the shape of that potential well kind of like the half kx squared to a first approximation, and you can use that to then determine the potential energy of a deformed bond versus an equilibrium bond. Okay. And so forth. Right? Okay. So, a lot of these, good question, all right? And this is great. I mean, it's one reason why I teach, right? It's like I get put on the spot, and then I have to think on my feet as to, right? Oh, you can put me on the spot. Perfect. No, I love it. I want you guys to ask questions, and I am confident enough of myself that I'm not afraid of revealing the edges of my knowledge. Of saying, if I don't know the answer to that, I don't know the answer, look it up, let me know, and we'll all learn, right? This is why I'm never intimidated about speaking with people. Like, if I don't know, I don't know. I don't have to pretend to know something I don't, right? But thank you for that. Okay, so that was potential energy. Kinetic energy is once the object starts moving, we have energy of motion given by this relationship, half mv square, velocity square. So the greater the velocity, right? If I double the velocity, then 2 square becomes 4. So the potential energy travel becomes like 4 times larger compared to if I were traveling at a velocity of 1 meter per second. I now move to 2 meters per second. My kinetic energy has gone up by a factor of 4 because it is 2 square, right? But all you need to be aware of is, again, just as a reminder, this is just half multiplied by the mass of the object multiplied by the velocity square. So if the object is, so the mass of a elephant compared to a mouse, the elephant would have a much higher kinetic energy than the mouse for the same velocity. Looking at this expression, is it possible for an elephant or a mouse, let's say, is it possible for a mouse to ever have the same kinetic energy as an elephant?
Is it possible?
Is it possible for a mouse to have the same kinetic energy as an elephant? Yes or no?
Yeah.
Okay, show of hands for no. Show of hands for you have no clue and you're not going to vote. One, okay. Show of hands for extra credit. Not that I want to encourage that, but I want to encourage the fact that you spoke up, if you will. And extra credit for yes. Okay, what do we have to do? How is this possible? We have part of the class that didn't raise their hand for any of the options. There are no options left.
You said extra credit for that.
Extra credit for what?
Yes. You said extra credit.
No, I didn't. I said extra credit to her because she had the courage to speak up.
Yes, you said extra credit for that.
Oh, I see. So people took that to mean, okay. Now you already have an extra credit, right? Here's an extra credit to you for speaking up. Okay. Okay. So the answer is yes. What do I have to do to the mouse to give it the same kinetic energy as an elephant that's kind of ambling along?
Make it go to speed.
Yep. Have it travel much faster, right?
Possible, but not probable.
Make the mouse very dense? Is that what you said?
What?
I misheard you. I thought you said make the mouse. I thought you said make the mouse very dense. You could do that.
The mouse would have
Compact
to
the
move-
mouse.
The mouse would have to move extremely fast,
That's right.
faster than a mouse is capable of moving. So it's not probable for a mouse to have the same kinetic energy as an elephant, but it's possible if it had help. Like if it was shot out of a gun.
You've never seen a mouse.
Just putting a...
You've never seen a mouse shot out of a gun?
What?
You've never seen a mouse shot out of a gun?
Can't say I have. No.
Okay, good. I mean, don't they do that in circuses? Like put a human in the cannonball thing, right? They can do it with a person. They should be able to do it with a mouse, right? Okay. So, but you're right. You'd want the mouse to be traveling much faster than the elephant, right? And so, if you said that a mouse is like, if an elephant is 2,000 times the mass of a mouse, you take the square root of 2,000 and whatever that number is, so that's 10 multiplied by square root of 20, so it's like 10 multiplied by about 5-ish, so it's about 50 times. So ballpark, the mouse would have to be traveling like 50 to 60, something like that, times faster than the elephant. That's all. That should be doable. And you have to train the mouse. Yes. Okay, so here's an illustration where you have whatever, a garbage can and an anvil. Do not do this experiment at home, right? That's tied by a rope over a pulley or whatever. So now you have potential energy of this anvil, right? Because it's up this potential energy, mass multiplied by gravity multiplied by height. This expression applied to the anvil, right? So mass of the anvil multiplied by the acceleration due to gravity multiplied by the height of the anvil above the ground. It's the potential energy. Now if you were to cut the string, what happens is this anvil starts coming down and the potential energy gets converted into kinetic energy. Anvil accelerates, traveling at a high speed, and hits this can and crushes it, right? So this was an example where potential energy mgh was converted into kinetic energy, half mv square. So by equating the two of these, you should be able to figure out, if you know the height from which it's falling, you should be able to figure out the velocity of the object, right? mgh equals half mv square, cancels out the m's, 2gh square root gives you the velocity. I mean, in principle, I'm not asking you to be able to do it for this course, but I'm just letting you know how you would do it, right? I see looks of alarm. Okay, roller coaster, or in this case, here's a woman with what looks like a longbow. I'm presuming I don't arch, so a longbow. If it's a different kind of bow, let me know. So what happens is, as she pulls the bow taut, right? She's pulling the string back with the arrow. Her energy ATP converted into ADP, right? That energy is being converted into potential energy, in this case, of the bow. So the bow is being stretched, right? And is under tension, so that's converted into potential energy. When she releases, what happens is the string snaps back, the potential energy of the bow gets converted into kinetic motion, kinetic energy of the arrow as it travels to its target. So again, that would be potential energy of the bow converted into kinetic energy as the arrow travels along. Roller coaster. So if you look at the cars up here, right, from down at the bottom of the coaster, they travel to the very top. What happens is at the very top, they have a potential energy mass multiplied by gravity. Mass of the cars multiplied by gravity, which is 10 meters per second, multiplied by the height from the ground. As these cars come down the roller coaster, all of that potential energy gets converted into velocity. So where do the cars travel the slowest? At the top of the roller coaster, at the halfway point, or at the bottom? So, okay, let me rephrase the question. The cars in a roller coaster, are they traveling the fastest at the top of the roller coaster, or at the midway point, halfway down, or at the very bottom? Did you all have deprived childhoods? I had a deprived childhood. I did. Sorry? Okay, so let me rephrase the question for the rest of us. Roller coaster, car at the very top. Is it traveling the fastest at the top, or at the halfway point downwards, or at the very bottom? Fastest. Have none of you been on a roller coaster? Were you sleeping when you were on the roller coaster? Fastest. At the bottom, right? So two of you go with fastest at the bottom. Any person wishing to differ? To disagree? On the way down? Extra credit to you for having the courage to speak up. That's totally awesome. More power to you. Jenna, right? Okay, great. I was afraid that all that non-alcohol that I drank made me lose all my memory, right? Okay, good. What happens is MGH at the very top, it's all potential energy. When it's coming down here, half of the potential energy gets converted into velocity, kinetic energy, and it's at the halfway point. When it gets to the bottom, all of the potential energy is converted into energy of motion, into kinetic energy. So the cars are traveling the fastest at the bottom, which is what you would see when you happen to be on one of those.
So if you have a person of more mass on your roller coaster, it's better? Like you want more weight, you want a bunch
No, actually,
on the roller coaster?
it turns out that the mass cancels out because you're equating the two of these. MGH equals half mv square.
Oh, gotcha.
So the m's cancel out, and you just got the GH and the v
So
square.
it's the height.
Yeah, so on Earth, it's just the height that makes the difference to the velocity. If you were to be on a heavier, like a more gravitationally attractive planet, so a planet that's denser, for instance, then the velocity would be higher on such a planet. But on Earth, it's just the height that makes the difference, right? Good, glad to see that application. Okay, introducing the work energy theorem. Work energy theorem basically states that the work done on an object is equal to the kinetic energy of the object. So you put work into your car, as you push it, that gets converted into a change in kinetic energy of the car. The car is moving, let's say the car is stationary, you start pushing it. Once it starts moving, you now have kinetic energy, right? So that change in kinetic energy from the zero, no kinetic energy, to now it's moving, having kinetic energy, that is equal to the work that you put into it. If you put in $10 worth of work, you get $10 worth of kinetic energy, assuming that there's no friction. Okay, introducing another law, which is probably one of the most established laws in science, is the conservation of energy. Conservation of energy states that energy is conserved. Energy cannot be created or destroyed. So in any, from a philosophical viewpoint, I'd have to modify this law. This law is incorrect. But from a physics viewpoint, we accept this law as stated, right? But from the viewpoint of philosophy, the law is incorrect. I'll leave it at that. But, sorry?
I don't want you to leave it, but I was wondering if you would.
Okay, how about I'll comment on this at the end of the lecture, right? Extra credit to you for speaking up and asking, right? So, from a physics viewpoint, energy cannot be created or destroyed. It can be transformed from one form to another, but the total amount of energy never changes. In principle, it's like the amount of dollar bills in our society, right? Like you happen to have a dollar bill in your wallet, you go and get a burger or whatever, and you pay the dollar and you get your burger. The dollar is not destroyed, right? Neither did you create the dollar. What happened is just it moved from you to somebody else, right? So the dollar is in circulation, it has neither increased nor decreased, it's just moved to somewhere else. So similarly with energy, the idea behind conservation of energy is energy, when I drop this, like for instance, when I lifted this block, what happens is, let's say the block were on the floor, right? So the block is on the floor. When I lift it up, what happens is, see, the block doesn't have any potential energy now. So I bend down, I lift it up. When I lift it up, the block now has potential energy. Where did that energy come from?
From your work you did on it.
Yep, good job. Extra credit. It came from me. It came from work that I did on it. Force multiplied by distance, right, was the work done. That became equal to the energy of motion that then came to a stop, converted to energy, potential energy, right? So now when I let go, that noise, that acceleration of the object is really ultimately energy that came from me. It came from ATP in my body that just got converted. I used up some of my ATP. It's like all ADP, poor things now, right? So I'll have to go and like feed them again at some stage. So notice that in that case, the energy in the system did not change. All that I did is I transferred some of my energy from ATP into the potential energy of this object, which then got translated into kinetic energy that went off as heat and sound waves and so on, right? So that's what conservation of energy is about. Okay, so here's an application or a